Right.
All right, let me pull this up. Oh, hang on a second. Beautiful. I want to. That's good enough. Okay, hi everybody. I'm Doug Endrizzi. I'm an experimental scientist at Real to Fusion, and I'm still a zero-time fellow at UW-Madison. I work mostly on the WHAM experiment right now, and I'm a former UW-Madison PhD student. And I think you're going to hear a lot of that university pride in this next little bit of this talk. I was invited to give this after we hosted a workshop earlier this spring focused on neutrals and impurities, classic challenges of all laboratory plasma experiments. And I'll get into this in a little bit in the motivation for doing this. So let me start by just saying there's no place like Madison. Madison, here's the university campus. There's this lovely terrace out here, and we've got three fusion experiments on campus: MST in the physics department, HSX in electrical engineering, and Pegasus in nuclear engineering and engineering physics. Those are 3 blocks apart from each other. Pegasus, HSX, and MST, and then if we advance a slide, then we've got campus up here. We have our 4 lakes, the watershed, and down here is WHAM. So a 15-minute drive south of campus, and we WHAM. So there's 4 fusion experiments on campus, and the quintessential Madison PhD experience is you get really excited to go to DPP. You travel 1,000 miles. You're like, oh man, I'm gonna meet somebody who's going to be able to answer this very specific question I have. And then you go to the poster session, and the row over is somebody from HSX, for example, who has done this 20 years ago. And so Madison really has a lot of experience, and we run. There are regular colloquia and seminar series as part of this between the 4 departments that host these fusion experiment or plasma experiments. But often those are really focused on the pure plasma physics questions. So when we have colloquial speakers coming, they're not talking about, some very obscure vacuum issue. With that motivation, we decided to do a workshop together early this spring, which was just focused on the really unpublishable vacuum and impurity practices that each of these groups has developed as just an opportunity for us to share information among ourselves. And so now this is posted on this website. So this is Whipple, the Whipple webpage, which is showing the big red ball and MST right here. And you can go and there's a neutrals and impurities tab there. And we just hosted a second one. So all of this presentation material is basically in there. So if there's anything from this that you want to look more at, go check that out. That's what it's there for. Right. So we hosted this one-day workshop, and this was divided into sections, talking about vacuum neutrals and then talking about dominant impurity species and the challenges that each device faced. And you can see from the titles, we were trying to keep it a very informal opportunity for just free discussion sharing. And I even saved notes from that. So that was UW. I want to share a very good resource that came out or that I became aware of this year. Earlier this year, Real to Fusion invited Kurt Lesker, the company, which has an education wing. So here on their webpage, there's this vacuum education tab. And they came and did 2 days of workshops on vacuum hygiene and vacuum system design. And there's a lot of stuff in there that is not intuitive, and some of it I had known before, and some of it I hadn't known before, and certainly hadn't put some things together. So, highly recommend that you guys or anybody invite them to come to your campus and give these presentations. Plasma physics isn't the only one who does vacuum stuff. There's lots of chemistry research that needs vacuums and vacuum equipment. And so if you don't have enough people to make it worth it for them to come out, then invite your chemistry department. There will be a lot of value that comes out of this. So what do I want to do? I want to just share 3 unfortunate truths that are just a nice reality that we're dealing with. These are all slight paradoxes. The smoothest surfaces are actually atomically very rough. The best lab vacuums are bad, and most gases are sticky. These are just unusual things that make our life really difficult. So here we've got an example from this 2020 Nature Physics Journal paper where they were looking at electropolished surfaces and their surface roughness. So this is just a generic paper. There's lots of things like this. Most people have seen this where even very smooth surfaces actually have pits, dents, holes, things in them that really drastically increases the surface area of those surfaces. So here we're not even zooming in down to atomic scales, but there's a lot more surface area than just a nice flat surface. So that's a challenge. Good. The second point of this is the best lab vacuums are bad. So just crunching numbers for myself this morning, 6 times 10 to the 23rd molecules in a mole. 1 mole is 22.4 liters. That's 760 torr. And so if we take a reasonable laboratory vacuum, 1 e to the minus 7 torr, the molecular density is 3.5 times 10 to the 9 per cubic centimeter. So 3 billion per cc. And there's a lot of space plasma physics people on this call. And so everybody knows density of the solar wind at 1 AU is 1 particle per cc, right? So we are a long way off of that. And then the last thing that I really didn't know is that most gases are sticky. So all gases can physisorb or undergo physical adsorption to the surface of materials. So here we're talking about dipolar non-chemical bonds, van der Waals type interactions with binding energies that are at least an order of magnitude less than the weakest chemical bonds, where you're really swapping electrons. So here things are just polarizing a little bit. There's some weird electric fields on the surface, and they can hang out there in this weak bond. Here we're talking about stuff that's 1 to 10 kcals per mole. And then that means that one physisorbed nitrogen molecule will stick around for a relatively long time before it releases from the surface. So you've got a clean surface, nitrogen molecule comes in. It doesn't just specularly reflect necessarily. It can often just stick there and hang around before it jumps off. So these are slides taken directly from the Kurt Lesker presentation. And so just more support for inviting them to come to your campus, talk about all of this research. Here is showing the mean stay time, the dwell time, the residence time for adsorbed molecules, molecules that have stuck to the surface. They're not penetrating in, and they're not chemically bonded. Well, sometimes here they actually are. So stuck to the surface at 300 Kelvin for various values of this energy. So here you can see these typical gases. Helium is our least likely to stick to the surface. Most people here just know that intuitively. And then we have hydrogen, argon, nitrogen, carbon dioxide. Water's not shown here because it's a little bit more complicated. And then we have chemical absorption here, where we're above 10 to 20 kilocalories per mole. So what's important here is let's look at hydrogen. So molecular hydrogen is saying here it's got a residence time of about 1 times 10 to the minus 12, 1 millimicro nano picoseconds. And since a hydrogen molecule is moving at like 2 kilometers per second at 300 Kelvin as a thermal temperature, that means that it can traverse 4 ion atoms in that time. So this is actually sticking and holding there in the time that it would normally cross 4 other atoms. So this is weird, right? This is a property of all gases and these surface bonds that get weakly formed. So here, also from this Kurt Lesker presentation, are results from a much older, I didn't add where this was from, but a much older experiment where they have a beam of helium coming in and it's striking a platinum surface. And on the left, we've got, and then this is the intensity of the reflected neutrals as a function of normal incident angle. And so here they're striking this oblique beam with 35 degrees Celsius, 35 degrees. And this temperature on the left is at room temperature, I believe. So room temperature collimated beam, not sure how they did that. And then a room temperature platinum substrate. And then over here, we've got a hot 1800 Celsius beam striking like a 1300 Celsius target. And what you can see is that it's not pure specular reflection. If it was pure specular reflection, those atoms would come in this way and they would come right off like that. But there's some spreading to that beam, and it's not aligned with the incident angle. And even at very high temperatures, right, helium is our least likely to stick. Even at this, you still see this contribution of atoms that have stuck to the surface and then released with some random phase angle that ultimately leads to this cosine distribution of emission right at that on the axis there. And so this is just evidence of this weird interaction. And so if you take this, if we're thinking about these rough surfaces, and we've got a helium atom coming in, and it does specular reflection. Well, it actually is going to come off on some odd angle because surfaces are actually rough. And then they can get trapped in these holes. And if you add on to that the fact that at each of these, there can be a resonance time, a dwell time. It's not pure specular reflection. Each one is this cosine distribution. Then you end up with something that takes a lot longer. So if you take these three unfortunate truths, the smoothest surfaces are actually rough, the best lab vacuums are bad, and most gases are sticky, then you end up with this reality that monolayers of adsorbed gases very quickly build up on clean vessel walls, even at ultra high vacuum. So they have this table from their website, which is that here is the pressure and then the number density of particles, the mean free path, particle flux, again at room temperature. And then this is the time for one monolayer to form. So if you have a vessel wall where you've managed to liberate all of the neutral atoms that were physisorbed to the surface, and so it's perfectly clean, how long does it take one monolayer to form? And you can look down here at 7 times 10 to the minus 6. This isn't a good lab vacuum. That's saying it takes 0.3 seconds until you have a monolayer of neutral gas all over the inside of your vessel. So this was shocking to me when I learned this. The point here is if we go 2 orders of magnitude lower to a reasonable good 7 times 10 to the minus 8 torr vacuum, that's only multiplied by 100 gives us 30 seconds, right? This is 0.3 to 3 to 30. That's only 30 seconds for this time for one monolayer to absorb. So for example, if you just did some cleaning, a pulse discharge cleaning, and then you wait 30 seconds and you've got a few 10 to the minus 8 between shots, you can build up those gases back on the surface. So this was shocking to me. But this is part of the motivation for why all of these these plasma experiments have to work hard on their vacuum. So here we're looking at a picture of WHAM in the upper left, HSX in the upper right, Pegasus in the lower left, and MST in the lower right. So these are all the fusion experiments on campus, and we have a simple axisymmetric mirror, helically symmetric stellarator, a spherical tokamak, and then MST as a reverse field pinch. So these are all really different devices. And one of the things that came out of this is that they all can't do the same things, but we've all developed kind of similar behaviors over years in learning how we needed to condition our vessels. So anyway, there's no place like Madison. So here is MST. MST is a really unusual experience. And let me say that at this point, I'm going into slides that were put together by each of these groups. So this one right here is from Joe Flahaven, a graduate student still on Madison, excuse me, at MST. Right. So MST is a really unique experiment in that there are just two halves to the vacuum vessel. So there's this top half and a bottom half. And on the outside, this is an electrically conducting so that current flows through the shell like this, producing a toroidal field. So it's a single turn transformer for producing the toroidal field. And then for driving current in the plasma, they have this huge transformer going this way. But if you had this shell that went all the way through, then that would just drive current in the shell. So what they have to do is actually on this side, the transformer core is gapped. So the shell, the vacuum shell, has a gap there. And what that means is that you've got one O-ring seal here, and then another O-ring seal in the poloidal direction, and there's a junction that needs to be made in this vessel between two O-ring seals. So there's this O-ring T spot right there, and that was how this was done. It's operated like this for a long time. It was a very clever solution, but it's an O-ring seal. So of the four experiments, MST has the worst base pressure of these four. That doesn't matter so much because their plasmas are actually pretty big. So let's go into this. Actually, I don't think I have this here. Yeah. So the major radius of this is 1 meter, and the minor radius is half a meter, 0.52 meters. So this is a meter radius, meter diameter, and a meter radius plasma. It's a big plasma. And with that, that means that neutrals from the edge really have a hard time to penetrate through all of that plasma to get in the core. By having such a big device, they can tolerate uh, vacuum conditions that aren't as good as at some of these other ones. Um, right, MST can operate in a bunch of different scenarios. Here we've got examples of electron temperatures that it can reach in these different scenarios and the voltages that are around it. What I want to show are, here's a picture of inside of this vacuum vessel. So you can see this is actually the aluminum wall that over the time has been coated in all of the plasmodium, the crud that got redeposited from elsewhere. And so this aluminum wall, there are graphite carbon tiles. And then over the years, there's probes like this, which is made out of boron nitride. And you can see that that's been metallized on the surface, but there's definitely parts of that have come into the plasma too. This also, a long time ago, they did boronization on this machine for conditioning purposes. And what I want to talk about is what they actually do for cleaning their vessel. So, of the main strategies to get good vacuum, um, they have to deal with the fact that they've got this O-ring seal and this T-joint, which has a bad leak. Mel, I see you got your hand up.
Yeah, sorry, I have a question. Can you describe
Go for it.
boronization for those of us who are not fusion people and don't
Oh,
do that in our machines?
totally. So, um, boronization, the idea is you want to have the lowest Z materials as your plasma-facing components. So, the way that there's a lot of ways to do it. Some experiments will drop a little bit of boron powder from the top and it'll fall down into the plasma. And then that gets ionized as part of the plasma and will redeposit on the locations where the plasma touches the wall or just kind of everywhere too. And that means that in future shots, the stuff that's getting ablated off from contact with the plasma is boron, which is just much better than, say, aluminum, which has a lot more electrons and can radiate a lot more power out of your plasma. So the way that they did it on MST, there's lots of ways to do it. They didn't ever use a powder dropper. Maybe they did, but I don't know that. They used diborane. So they would use a gas, they would inject a gas and then break that make plasmas out of that gas, I think. And there's actually more details of that in this presentation, so feel free to check that out online. Um, yeah. So they boronization is one method for controlling impurities and for controlling impurities. Um, Sorry, what do I want to say? Oh yeah. So MST can't do other things like titanium gettering, which is another traditional uh, neutral pressure control technique. And instead, they do pulse discharge cleaning. So anybody who's ever been in Chamberlain Hall where MST is held overnight will know that there's this every 5 seconds, there's this pulse that happens throughout the building, and that is the MST vessel on this automated pulse discharge cleaning cycle. So it'll do 100 kiloamp, 3 millisecond pulses, and they run that overnight. And they, over the years, got it so that it runs without operators. And then in the morning, their vacuum vessel is clean and they're ready to go. Sometimes they'll run it during the day or they'll do other conditioning shots in it. But I think this is a good example of one of the best ways to condition your vessel is running more plasmas. So that's ultimately what they do. And these were Joe's summary notes. Aluminum wall is the biggest source. They no longer do boronization. And the plasma heat flux to the walls liberates impurities. And so they do surface cleaning with their own plasmas. So that's MST. Pegasus 3 is the spherical tokamak on campus. And so here's a cross section of it in this new upgraded 3 iteration. This has a much smaller major radius. This is 0.5 meters here. and a small aspect ratio, right? So it's a really squat tokamak, and it still has reasonable magnetic field and reasonable total current. Densities are 10 to the 19, and right now, they're at 50 eV. They they test local helicity injection and coaxial helicity injection as methods for making and sustaining the plasma without inductively driving it. And they're also working on this microwave assist for that. So just going off of this, their vessel uh, is substantially big. It's much nicer than MST in that it's all stainless steel, and there's very few O-rings, if there are any O-rings. There might be one at the ceramic break. I actually can't remember that off the top of my head. But they use both turbopumps and cryopumps and titanium gettering. So this is one of the things that really lets them get down to the 10 to the minus eights in operational pressures. So titanium gettering, for people who haven't done it before, you take this titanium slug and you heat it up. You get it into the point where it starts sublimating, and then elemental titanium comes off and deposits on the walls of your vessel and on other probes and everything else that's there. Um, and then that titanium very happily forms titanium oxide, titanium hydride, and titanium nitride. So pulling out oxygen, hydrogen, and nitrogen is great. Those are some of the dominant impurity gas species, and so titanium does a great job for getting rid of those. One thing that's really interesting about Pegasus is they actually don't do it either between shots or in the morning or overnight. They run it continuously. So they run it during their plasma shots. So here, this is a point from uh, um, Sophie Red. Oh, I don't have her name on here, but yeah, her presentation is also available online. Um, they've got a continuous source of titanium that's just sublimating and passing through the plasma. So they always, when they have this on, they have this additional source of titanium from the sublimators themselves, not from the plasma touching the wall and liberating more. They also do glow discharge cleaning. So if I'm remembering correctly, I don't believe that they bake their vessels. They will just glow discharge clean. So they do, after a vacuum vent, a long glow discharge campaign. Here they've specified it as 20 hours of hydrogen and then 100 hours of a helium glow discharge. And so here they're using both the temperature and the UV to break water off of the walls. So here, when we were talking about sticky gases, water is a very sticky gas because it is a polar molecule. And so having all of this power coming out is what's helpful for pulling that water out. So I can't remember whether this is from, I don't think this is from their experiment, but I could be wrong. Anyway, they do this for a long time. And then they also have to condition other parts of their vessel too. So in summary, they are operating at 10 to the minus 8 torr. They use a lot of titanium gettering very successfully, and think that they're getting to a very low neutral density and with a high recycling coefficient. Good. All right. So two down. We've got HSX next. Oh, I think this video is going to work. All right. This is super cool. So this presentation was from Thomas Gallenberger. And what this shows is the 4 segments of the HSX vessel and how they have to come together. So at each of these joints, there's an O-ring seal between these 2 parts of the vessel. So if anybody doesn't know this, this vessel is incredibly interesting. To make this, they explosively formed it. So they made a mold, and then they put a pipe inside of that mold, and then they put explosives in that pipe and exploded it until it fit that mold shape. So that's pretty good. But they have to be very careful about how they heat their vessel. So one of the things that HSX does is they do try to bake their vessel to get rid of water from the walls. That is a challenge for having a vessel that's made like this with lots of very unusual welds around it, and to have these O-ring seals here. If the differential expansion is too much, then you can form leaks. One of the other challenges of having this stellarator is that they currently don't have cryopumps. They only use turbopumps, which means those turbopumps need to be far away from their magnetic field. And the region between these magnets, you can see, is not a lot. There's not a lot of space. So they have to have these long tubes that connect their turbopump to their vessel. And after the Kurt Lesker presentation, you should think about, or I now think about gases that are traveling down this tube. Um, every time they will stick to the wall and hang out there for a little bit, and then they're going to release from the surface with this cosine distribution, and then they might bounce this way, they might bounce backwards, they might bounce forwards, and then they're going to stick again, and then they're going to bounce again in some random direction. And so having a really long, narrow tube like this is bad. What you want is you want your pump right there on this, and they can't do that because of these stray magnetic fields from from the magnets. So huge challenge that they have to deal with. So they are instead they work on baking their vessel. So here on the right is a CAD diagram where each of these gray sections is a set of heater tape. This is designed to go to 150 degrees Celsius, which most people will remember as the like limited temperature for Viton O-ring seals. In fact, they actually only operated at 60 C because in practice, this is such a difficult vacuum vessel to make it heat uniformly without popping a weld they limit themselves there. So they will do a very long thing. So after a vacuum vent, they will bake their vessel from anywhere, basically up to 2 weeks. So this is standard practice around a lot of the tokamaks of the world, except they want to go to high temperature. So rule of thumb, most reaction rates double every 10 degrees Celsius. So when you go from 60 to say 100 C, that's 2 to the 4. And if you go from 60 to 150 C, that's 2 to the 10. So it's basically a 1,000-fold increase if they were able to get to 150 C. So these baking times wouldn't be nearly as long if they could go to much hotter temperatures. But that's a big challenge. So one of the other things that HSX really struggles with as a stellarator is the cross sections for a lot of these plasmas get quite thin at points. So here we're looking at a model of neutral gas injection at this one point and how it diffuses around the vessel. And this is with a plasma absorbing it. And so you can see that it's actually neutral penetration depth is really deep. And this is a challenge if you've got hot ions, which will want to charge exchange out and leave your plasma. So this is a really big challenge. And they've done a lot of things over the decades. I think dang, I took out the slide. So Alexis Wolfmeister, her presentation on this talks about the carbonization and boronization that they had done in the past. They currently actually run with clean walls. So this was an interesting lesson. They ran with both of those separately at different times. They both worked well. And then ultimately, there was too much material that had deposited onto the vessel wall. So over time, too much boron built up that they would get dust and flakes coming in. And that's really kills your plasma performance to have one little dust mote that's got the same number of particles as your entire plasma in it, or way more, fall into your plasma. So they stopped that. They cleaned their whole vessel. They run with a bare steel wall now. And they're going to a new configuration soon. All right, the last one is WHAM. So WHAM is a simple mirror experiment. There are two high field magnets in these two brown-orange colors right here. The plasma is trapped between those regions of high magnetic field and then escapes through the mirror throat out to the end cells. So here we've got one vacuum cell and this other end cell. This end cell was actually one, and this was part of the oh my goodness, I'm forgetting the name of it. Out at Los Alamos National Laboratories, there was a Spheromac experiment, and this was the vacuum vessel for that, and had just been sitting outside for a little while, and we were like, we'll take it. When Kurt Lesker came, their very first piece of advice to everybody was never take somebody else's vacuum vessel. It sounds like a gift, and it's almost never a gift. It's almost always a curse. And so one of the challenges with this is there were lots of ports that over the years had opened up small leaks on them. So when we first tried to bake this end cell, this north end cell and the south end cell, we didn't keep the temperature perfectly uniform, and that was too much stress on some of these weld joints. And so we popped some welds and had to go back in and redo them. Um, right. WHAM is like HSX really struggles with small plasma sizes. So if we have a plasma that's approximately 26 centimeter diameter, and we have fast ions. So here is a depiction of a 7.5 centimeter deuterium ion that comes in from our neutral beam system at 20 to 25 keV. That's its gyro orbit, right? So that's for one that's perfectly at the center. If this is over here, while it might still be in the plasma, like in a high density plasma region, it's sampling out into the edge where the neutral density is very high. So this leads to, if you've got a reasonable neutral density in the edge, this leads to very rapid charge exchange with that neutral gas. So it's very important at WHAM that we keep this neutral pressure as low as possible. So we've this presentation was done in May of this year, and since then we've done another baking, glow discharge, and cleaning campaign to try to see how well we can go in our base pressures. So when we first did it, we baked for 3 days. This last time we baked for 3 weeks. Um, and and then this was a glow discharge recipe that was led by one graduate student here, Kunal Sanwalka, who I didn't have his name on here, but he is the one who made these slides for WHAM. Um, they do, or we now do a hydrogen followed by helium glow discharge cycle, and we've also done this with hydrogen followed by neon and hydrogen followed by argon, I believe also. Um, and that is also really important. So we found that glow discharge cleaning works really well, except for when these HTS magnets are on, and when we run them, we keep them on for months at a time. When those magnets are on, you can't blow discharge clean in the normal way. Normally, you stick some electrode in and you bias that electrode with respect to everything else. The plasma forms the plasma is a plasma. It fills the volume of the container and it forms a sheath along every surface. But if you stick an electrode in here with the magnetic field on, it's only going to follow those magnetic field lines and it will only form a plasma along that flux tube. So that's a challenge if we want to try to say clean all of this vessel wall that's over here. So yeah, we can glow discharge clean, but we have to have our magnets off. We do baking, and those are really both essential for good plasma performance. So goodness, I don't even have my watch on and I can't see the time on here, but I'm wrapping up at the end. So here are just some really simple lessons. Uh, I don't think I need to go these. I'm just going to leave them up here right now. But I will remind everybody that if you want to look at any of these presentations, it's available on that Whipple webpage at the University of Wisconsin. So yeah, there's no place like Madison. This was really great to get all of this experience together and to have people talk about this. So thank you, everybody.
Right. Fantastic. Thank you, Doug. I have more questions, but I will let the other people in the audience ask questions first if they'd like. So either raise a hand and unmute yourself or post it in the chat if you don't want to unmute yourself. Well, no one else has questions. I will ask mine. So you had talked about when talking about the boronization, you want lower Z impurities if you have to have impurities, so you lose less energy to the radiative losses there and like ionizing those. And that makes sense. But then with the gettering, you're dumping titanium in, and I know like the end goal is for that to bond with the other impurities that you don't want, but like, does that work because the timescales for that reaction are faster than how you're losing energy to the titanium ionizing in the plasma? Or
Hmm.
how does this become a net win?
Yeah, so that's a great question for HSX specifically. And I think they would make that argument that, hey, the numbers, while it looks like there's reasonable numbers of particles that are coming through their plasma, this contribution is actually small since their plasma volume is sort of a cubic meter. And so if you've got something that's 1 millionth of the number of particles, and like, okay, that's a tolerable amount of particles coming in. And the other difference is here, the titanium is coating everything. But I think I don't know if they tried to shield their plasma facing components. So like the whatever limiter they're really using, that might not be getting coated in titanium, right? That might just be getting cleaned by the plasma. Um,
Okay. Yeah, that would make sense. I suppose too, once it's on stuff, it can do some of its work between shots, preventing whatever leak is still there by bonding to it
mhm.
stuff and
Yep.
getting that out. Okay, cool. Joe, go ahead.
Yeah, Doug, good, interesting talk. I had sort of two questions. The first was at the beginning. You sort of got to this. You mentioned unpublishable results, right? I was wondering uh, if you feel like there's a place for this sort of institutional knowledge of these various experiments. Is there a place where these can get published somewhere? Does it need to
Yes.
be in like special issue of
Nope.
RSI or something like that? Like,
There is a vacuum science journal, right? And so like there is a journal for this stuff. The challenge is we as a field, as a discipline, have a bias from valuing those things. And
hmm
so I really can't imagine many of the advisors talking to their students and saying, "Oh yeah, this like really minor thing, go publish this in the vacuum science journal," right? They want them to stay focused on plasma physics stuff. So this is something that we should just be aware of, not necessarily bad, but certainly a challenge in that I, out of my PhD program, hadn't really grappled with some of these challenges because each of these experiments solves them in different ways, and they're they're more deleterious for some than others, and so I just didn't really fully appreciate how difficult some of this stuff is.
hmm Yeah. And I guess to your comment, right? These small experiments or these smaller university scale experiments, right? Like that is where the advisors, the professors ultimately have sort of the final say in a lot of this, right? And it is kind of like you kind of live and die by the big impactful papers.
Mhm.
Yeah, so my second one, this one can be pretty quick. I've heard and seen some ideas for some of these future fusion pilot plants or whatever in using sort of like liquid metal first walls. I was wondering how much more complicated does that get? Does this get with a liquid metal wall rather than just a stainless steel or aluminum wall?
Yeah, liquid metal is so attractive in theory. If you have a fluid flowing lithium wall, it can make lithium hydride. And so if you've got, say, um, hot ions that are hitting that wall that would normally sputter that material, um, they certainly can still. I actually don't know if they can sputter droplets on, but they can penetrate into that and they can just bond. They can just get absorbed. And so there's a lot of people who are working on those liquid metal for plasma facing components for some of those advantages that it acts as a hydrogen getter, a neutral getter on its own. Um, and yeah, you can continually replenish it. And so, yeah, it is very attractive. But there's a lot of challenges with it too. If you want, next time you see, actually, there's a bunch of people on campus who have done liquid metal experiments, and so they can talk to you about that. What I've heard from them, for somebody who worked on uh, the lithium tokamak experiment LTX, talked about going into the vessel and having to scrub lithium nitride off of the vessel walls, which is just some brown crud, and they had to spray, just acetic acid onto it to get it to come off, and then just take a scraper on it, right? So, um, yeah, it will also produce plasmodium and gunk that builds up elsewhere in your vessel.
All right, we've got two questions in the chat. The first was from Chris Marcus asking if your cold or hot cathode gauges require iron shielding, like a clamshell,
Oh, yeah.
to protect them from fringing field effects.
Yeah, totally. So, um, all of these experiments have to deal with that. Oh, I think actually I'm going to go to my very last slide. So, going into reading these presentations, and even the notes on it is still interesting. There was one good bit of history, and I think it came from HSX, but it might have also been at Pegasus, is that you want to have multiple overlapping pressure gauges that work with different mechanisms. And I see a lot of people nodding. Different gauges will fail differently. And so some people had theirs get coated in plasmodium, and it took them a long time to realize that they weren't at a super good base pressure because the gauge was reading that and they didn't have a second measurement of it. Um, and so, yes, those hot cath yeah, hot ion gauge, hot filament gauges are difficult to deal with when you've got magnetic fields around. And so we are still dealing with some of ours to try to make them robust to fluctuating magnetic fields, and that's a big challenge. In this workshop, I don't think we talked about that challenge specifically so much, but I know the other groups deal with that also.
And then the second
Um,
question, oh, someone else is speaking.
yeah, I think you can go ahead. I can proceed after that.
Okay. Yeah.
Oh,
Our second question in the chat was from Ted Bewer from ORNL,
Hi,
asking
Ted.
if titanium gettering ultimately led to titanium X slag, dust, flakes, other stuff ended up in your plasma.
Totally. So that's a good question for Pegasus. They didn't talk about that, but they always see titanium in their plasmas. So it would be good, to Mel's question earlier, doesn't that lead to a problem? I think they always have some minor concentration of titanium. And we can ask them if they ever have major concentration events of titanium, which would be observable. They probably, and I don't know this, with a pretty new clean vacuum vessel, haven't gotten to that point yet. But that was certainly the point that HSX got to with carbonization and boronization. And I expect that titanium gettering will happen on that too, just from the experience that we have here. Dmitry Yakovlev, a colleague here, has talked about experience at the gas dynamic trap in Russia, where they also do titanium gettering. And yeah.
All right, James, go ahead and ask your question.
yeah, thank you, Douglas, for that nice talk. The first time I'm actually hearing to a talk which is specifically meant for a vacuum process and maintaining the vacuum and issues related to that. Thank you very much. Very interesting and informative. Now, I have a crisis in our lab. Like, we are using a cryogenic pump to get a vacuum for about 10 power minus 6 to 7 torr. That's what we aim for. We don't want anything below that. Um, but what happens is that we use a roughing pump. We get to about 5 millitorr, and the 5 or 1 millitorr, and then the cryogenic will take over after that. Uh, but recently we are facing a crisis that even though the roughing pump brings down to 5 milliliter, the cryo is not further taking over. And we give the access for the pump to the chamber, but it's not doing any job. So we are like figuring out what could be the issues with a pump that it's not doing a good job. So in this troubleshooting, could you give some tips or ideas or suggestions in figuring out where the issue is? And secondly, this presentation is very good. Is it accessible anywhere? Like, do you upload it anywhere? That's one thing.
Yeah. Oh,
And third thing is, I listened to You Raise Me Up by Josh Groban, a singer. You look like him. I just wanted to tell that.
okay. Thank you.
Right.
I hope that's a compliment. Yeah, let me just point this out right here. So all of these slides that I presented on are from this neutrals and impurities workshop here. So
Wonderful.
whipple.wisc.edu, and
Wonderful.
then this tab right here. And so you can have access to them there. The specific pumping challenges are um, you you should find somebody on campus who is dealing with those and has dealt with them before. The first things that I would if you were answering this honestly, you would say make sure that your temperature measurement is actually correct and that you're getting down to cryo temperatures, and
Okay.
then your surface is probably fully coated and you need to regenerate it.
All right.
And then if those don't work, then you need more help, and that's where Kurt Lesker is happy to come by to your campus, and they do consults like that. And on the whole, they're very excited to come to plasma physics groups because they're not chemistry labs. Chemistry labs destroy their pumps and vacuum vessels, and so I think they'll be happy to come by.
All right. Thank you very much. Thank you.
And I can also say we will have the recording of this specific presentation, including the questions, posted on the
That's wonderful.
MagNetUS YouTube channel as well. I will probably edit out sorting out the screen sharing, though. That doesn't need to go on
Thank you.
YouTube.
Thank you very much.
All right, and then we've got one more question in the chat from Chris again, asking how low the vacuum needs to go before you turn on the titanium, I assume for the gettering again. Is turning it off correctly important as the chamber is eh, is it turned off correctly as the chamber gets vented? Is this important in practice?
Oh yeah. So if that is hot while your chamber gets vented, then titanium will form titanium nitride and titanium oxide, and it'll do that very quick if it's very hot. So yeah, you cannot have that on while you come up to atmosphere. Yeah, definitely. And then the first part of your question was about
How
it
low the
cooling
vacuum
down.
needs to get before you can turn it
Oh yes, yes, yes. Um, we get up to our ultra high vacuum and then we turn the titanium pumps on. I think that's standard procedure. You're 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 using that to really take you the last step. It's a very powerful pump, but um, it will saturate quickly because it's only the surface area of your vacuum vessel. So it's a very fast pump, but it doesn't have a lot of capacity in that level.
All right. And then I will abuse my power as moderator to ask one more question, which is you mentioned that you had gone from 3 days of bake to 3 weeks on WHAM, and this was mostly limited by experimenter patients, which I'm very sympathetic to. But I assume if you're committing to 3 whole weeks, that's like there's a reason, and you either have seen or expect to see some significant benefit from baking for that long. So can you talk about
Yeah,
that a
right.
little
It
bit?
does it absolutely. It's a big cost, right, to have that vessel there for that long, not doing science, right? And it's getting better. And when you look at the big experiments, big tokamak experiments, that's what they do. They bake for a long time. W7X bakes for a long time. And this is about getting water to migrate out of your system. It takes a long time for us, here we've got this pumping duct here. And so if we've got um, water that's here and it bounces there and it bounces there and it bounces there, it's going to take that a long time to get out of the system. And it really is just that is the time scale on which vessels in general can clean up. And so it's a big cost. And I think finally we got to the point where we were like, this is the real cost. We can't cheat our way past this. You just gotta do this. Hey,
Gotcha.
Psychot.
Yeah. Great talk, Doug. And I was waiting for the end to move it off a little bit in that sense that you also have the BRB, as one of the Madison is awesome, in Madison is awesome. It's not
Mhm.
a fusion device in that sense, but since we are all connected to MagNetUS and a lot of low temperature plasma physics,
Yep.
and how is the vacuum things over there? Like, is it a little easier to work because it's not a fusion device, or
Yep.
any comments? There's Joy is also here, so.
Totally. And so Joe and I, when we were doing graduate
Mhm.
projects together, we would talk a lot about neutral drag at the edge, right? So this was originally a dynamo experiment where we were spinning the edge of the plasma, and that neutral drag was an important contribution to momentum balance in that plasma. Um, and But this is a big vessel, 1.5 meter radius, 3 meter diameter. For the wall temperature neutrals, they are not penetrating deep into the plasma. This is a effectively highly ionized plasma in the core. But if you get warm neutrals, so if you get charge exchange events, for example, on WHAM, this happens where a hot ion comes in or hot ions in the plasma hits a cold neutral at the edge. Now you've got this hot neutral. That thing can go around. If it hits the wall, it can reflect off as still a warm neutral, lost some fraction of its energy, but that can penetrate deep into your plasma, right? So it's not room temperature. Its penetration depth is big. Um, and so that was something we just didn't think about, or I didn't think about in my graduate program because we didn't have any hot ions, right? This was sort of TITE kind of low temperature plasmas. Um,
So you're lucky, you mean, in that sense, that you
yeah.
don't have hot. Because, one thing, again, this is just this is not a question in per se, but more like a discussion, just all of us to think together as a community, is that, I always, when you compare our physics experiments to theory, and we compare to classical plasma physics, right? Ion cyclotron, electron cyclotron, ion neutral, ion collisions, ion electron collisions. We tend to neglect electron neutral or neutral. Like we tend to neglect the presence of
Yep.
neutrals in many, many, many situations, collisionless plasmas, and I mean, I'm amazed that it works sometimes. But I think as experimentalists, we should more and more acknowledge that they are there, whether we want it or not,
Yep.
as we are talking about and you did the calculation of even at 10 to the minus 8 torr, it's they're not like 10 neutrals in the system. There are many. And so I don't know. This is like, again, when we show ion cyclotron motion, typically the first chapter of Frank Chen, I mean, I love
Mhm.
it. And he also told this to me in a conference. Like, you look at this spring in this in the picture of BRB, right? That yellow coil that going through. If you have a lot of neutral collisions, ions or electrons cannot do that. They get collided out of their path.
Yep.
And I think in our presentations and in our mind, at least in our psychology, again, this is like years of just not understanding what is going on.
Yep.
Is that those collisions are important to understand, all the paths, and like similarly to what you showed that if your ion gyro radius is not in the center but off, you have the neutral. So the neutral density profile in a machine is different from the ion profiles or electron density profiles, ion density profiles. And we should just think about it. So sorry, long,
Absolutely.
long,
Yep.
long, long drawn thoughts, but thank you for this talk because I think we should be aware of this more and more. And maybe, I mean, I don't know, in future MagNetUS conferences, we might ask you to come and engage our graduate students into these kind of discussions.
I think this could be a
Um,
worthwhile discussion because there's been a big focus on where the neutral cloud at the end of LAPD plasmas is and how that affects how we run our
ooh,
experiments.
yeah. Yeah.
So it's been quite
All
interesting.
experiments.
Yep.
Yeah, I
They're
also just wanted
also,
to unmute to highlight Joe responded a little bit more about the dynamo experiments in the text and mentioned that they were mostly affected, or they were the most affected by vacuum conditions because they could run at 300 plus kilowatts for 10 plus seconds. And so current experiments are much more transient, scales of hundreds of microseconds. And so it's less critical in that regime.
Mhm.
Okay,
Sorry, go ahead,
thanks,
Doug.
Joe. That's true
Great.
because
Yeah. Great
a
point.
lot of us do steady state experiments, and then the neutral density just climbs and stays there. It doesn't go because again, it's a balance between how much, I don't know, in the absence of any better word, how much gunk is coming into the machine through whatever resources, and how much you can suck it out. So the fact that our pumps don't suck enough, they're not. It's not bad. It's not good, but
Yep. Yep. Yep.
so. But cool. Thanks. This is good. Okay, I will probably shut up.
You're all good, Psycat. Doug, any closing thoughts or any final questions from the audience?
I didn't put this on here, but everybody should do this estimate, which is, if you have a monolayer of gas, I crunched the numbers in my head, which was you've got a liter volume, 10 centimeter cube, and if you've got a monolayer of gas on the wall, how much is that in terms of density? If all of that was liberated, what's the density of your gas of your plasma there? And it was like I can't remember the numbers, but it's at least 10 to the 3 more than like a 10 to the 19 style plasma. And so it's a huge, there can be so much gas on the wall relative to the plasmas that we traditionally make. So this is a big challenge to Psycat's point.
Cool. In that case, let's thank Doug again, and I will stop the recording.